Recording. Test, recording. Okay. Greetings. This is Chemistry in the AM. I'm your host, Mr. Shindelka. I'll be your captain today. Let's see. Tristan. Hello. Big shout out to Tristan. And Austin, if he's listening. Okay. We say NH4 would normally have a certain number of electrons, but once you say that there's this positive charge, we know that we can't change protons because you changed atoms. You must have removed an electron. That's the only way to get a positive charge. So what we're thinking when we hear this is that we have N, normally, 1, 2, sorry. I'm going to do this. N, and then 1, 2, 4. I'm doing this so it's disconnected. 5. Normally, H, there's 4 of these. They're all with 1, and they only want to, there's another bond. They only want to get to 2. Normally, nitrogen wants 3 bonds, right? Now, we have 1 electron missing. If I tried this as is, as we've seen before, we could have I'm just showing this here like this. We would normally have NH3 if we had a nitrogen-hydrogen compound. But I can't fit that 4th one in here, can I? Any ideas what to do? Because we're missing 1 electron. Take it away. There'd be space for a 4th bond. Does that make sense? So you kind of remove 1 of the electrons. Say, yeah, that's gone now. So here, I'm going to turn that into a single, just like we indicated there, and it'll now be NH4. Now, yeah, that's about as good as it gets there. Something missing though. If I don't indicate something on here, what do we need to do? Remember when we did single atoms that turned into ions? We put a box around it, square brackets. And we indicate this drawing of the NH4 molecule isn't a molecule, it's an ion. It's missing 1 electron, it's a cation. Now, does that sort of, it means you have 1 less electron to work with, basically. Yeah, maybe. Okay, we'll try the next example together. Cyanide. The word isomers afterward, but we'll concentrate on cyanide. Cn minus. That means -1, an extra electron to work with. So I'll wait till we're here, and you know what, I'm going to just get the isomers thing. It'll be too distracting otherwise. So I'm thinking I got a C. I've got an N. And I've got an extra electron to work with. Whizzing around stuff. Where is it going to go? Now, you ask yourself, carbon normally wants to have 4 bonds. Nitrogen normally wants to have 3 bonds. We're told we have this extra electron. Where do you guess we would place it so that these things then could bond together to work nicely? On the carbon. If we place the extra electron on the carbon, it now only needs 3 bonds, right? Now, triple bonds are possible. So let's draw that out. Whatever. I know it's a triple bond in between. Don't worry about the color coding. Now, nitrogen will have 2 electrons left over, and the carbon has 2 extra electrons as well. Now this is I put the dots on the side because I like to think of them as far apart as possible. If you put them on the top, like here and here and here and here, those will dissolve in a minute. You're fine. When they're on the side, it represents something more accurate to what the reality is represented by these waves. You can't look under a microscope, and if it's an English microscope, and see a C and an N. Because then if you were in a Russian microscope, they have a different alphabet, right? You'd see different atoms. They don't come out that way. But this is a visual representation of the cyanide atom. But I'm missing one thing. What is that? Charge brackets, yeah. When I say this has an overall extra electron, so it's an extra charge. Okay. I'll get you to practice with some of those. Now I did 2 things. But I'll first get you to isomers, and then we'll practice. Maybe I zipped up too fast. Isomers. Isomer. Iomer. Isomers. Okay. Am I good with the diagram part if I zip it up? I haven't heard any difference, so I'll assume that. So you've had a chance to try these structures. I gave 2 hints, triple bond, C3H4. I've got 3 carbons to work with. And I know I'm not putting any dots on these. Here we go. Because, just saying here, I'll just keep duplicating this. Undo. I don't want that, I want a handwritten. Boom. Boom. Okay. Try this. Boom. Okay, there we go. That'll be my second structure. I got lots of H's, but I know the H's are single bond. Now, H's are dead ends, we said, right? So I hope you realize the C's must be in a row. 1, 2, 3. I said one way to try it is have triple bonds somewhere. Now, this end carbon, how many bonds does it have left over? If it's already used up 3, has a 4th one. That's it, right? This middle carbon, because remember, you can only have 8 electrons surrounding, and each carbon has 4 signals, right? So this middle guy only needs 1 more bond. So I'd say it's probably going there. This end carbon here has 1, it needs 3 more for the other singles. Hey, that works perfectly. CH4. Or C3H4. Now, the other way to do this, the isomers, this is why we call these structural isomers. If I said, I gave you the hint, 2 double bonds. Well, the only place double bonds can happen is in between the carbons. You can't have a double bond to hydrogen ever, as we know. I look at the end. The left carbon has 2 bonds, it wants 2 more. Now, if you put your lines like this and this, or the other way around, that's fine too. It's probably more accurate to have them as far spaced out as far apart as possible. And I can attach those H's there. Now look at this, it's like a mirror image on the right-hand side. The middle guy already has 4 bonds, right? So it's done. So then I think, yeah, and it's probably like this. Does that make some sense? Okay. Do we get the idea of isomers using the same number of carbons and hydrogens or any other alpha? That's you can come up with different structures. Those are called isomers. So we tried this. We built these models and the 3D structure of a linear molecule here. 180 degrees. That's the only way those double bonds get separated. The next thing we're going to try is what we call Trigonal Planar. Now this one you can't do with your model kit. Now I just showed you a model of this, but for the benefit of the recording. BF3, B is an exception. It has 3 valence electrons, and it would look like this. So I'm giving you this one. F, 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 fluorine 3 times. And the angle, because it's a plane, it's flat, trigonal, planar, these are separated by 120 degrees. Okay? So that would be the example there. So I'm letting you know, if you ever see boron, that non-metal, just go with trigonal planar right off the bat. That one kind of needs to be memorized because it doesn't add up to 8. Now, tetrahedral, we'll try this right away, CH4. We know the Lewis diagram, but how do we draw that in 3D? So the Lewis diagram, I hope you remember, see 4 ways. This is what the Lewis diagram looks like. But that's not what it looks like in 3D. That appears like it's a flat thing going up 90 degrees separated. That's not a good representation of what's actually there. So to draw this 3D structure, I'm going to put the carbon at the center, as you can see from your model. And I'm drawing it like the way I'm holding the model here, where this straight up. This hydrogen here, I'm going to the left. Then, you remember how we represented out coming forward from the picture? Sort of like a ribbon. This means coming out of the board. Dash going behind the board. So that's one way. If you took out a protractor and you measured these angles, of course these aren't too precise, you would get an angle of about 109.5 degrees. Now, don't worry about measuring them. I'm pretty sure it's 109.5. So, the angle between every hydrogen, 109.5 degrees, okay? And that would be the same angle if you measured here to here, or even here to here, but it's 3D, so it doesn't look like it. 109.5. That's as far apart as those 4 items can be. It's kind of fun, isn't it, if you know? You getting this down too? Okay. I said you don't have to draw it. This is the way I commonly write it, but I said also you could have it represented different ways. The same molecule. If you looked at it straight on like this, I could say these are going behind the board. And behind the board, these are coming out. That's just viewing the model from a different angle, isn't it? Instead of like this, kind of like this. You see how that's, if you had 3D glasses, you'd be able to see coming over the board or going behind, right? That's what this represents. It's another way to represent the same thing. Don't be fooled if you see it that way ever. That's it. So now what? Are we good on this? Okay. What about NH3, Trigonal Pyramidal? We actually saw this the other day. So moving along, we saw this the other day and drew it. We'll draw it again in 3D. This time the electron pair, we're going to put those at the top. It's like a tripod. essentially the methane molecule from above with the top chopped off and a lone pair of electrons there. So that represents a three-part trigonal pyramidal. What do we mean by that? Triangle base pyramid. A triangle-based pyramid, right? If you can imagine wrapping this with cellophane on the sides or something like that, putting tape around it, it'd be a pyramid, right? Triangle-based pyramid. The Egyptians never did that. There was 4 sides. Okay, we saw this before, as I said. H2O. We're familiar enough with it, I won't draw it as a Lewis structure. O, I don't care where you put them. But the H. I'm going to draw it this orientation this time. Show, though, in your 3D structure that it's, this would be the representation of it, that it's a slightly, it's like approximately 109 degrees, 109.5. It isn't quite because the electron repulsion pushes it a little differently, but it's in that ballpark. It's definitely not a 90-degree angle. So there we have that one. Then what? Well, I'll pause in a second here. Are we good with bent? I'm going to just flash this on the screen, then I'll come back to it. Do the same thing with these molecules. And this is for the benefit of the recording. And then I'm going to pause or stop here.